So, what we have been doing and learning is finding the limit. And that deals with what's going on as your x coordinate approaches a particular value. And what we found was that f at x, that's what's going on exactly at that point, may or may not be the same as the limit as it is approaching. So we looked at some examples yesterday. Here, f at x would be the same value. So those would be the same. Here, f at x was a different value than what it's doing as it approaches. So just a reminder of that. All right. So we do have where they're equivalent. That was that first example I gave you. All right. This is what we considered a well-behaved function. If it is a well-behaved function, then it is considered what we call continuous. So let me give you an example. All right, let's say that this is when x is 2. Okay. All right, now, kind of the easy standard to follow of knowing if a function is well behaved, it is if you were to put your pen or your pencil down and you were to trace that graph, you would never, ever, 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 ever lift your pen or pencil up. Okay, that's what we would consider well-behaved and continuous. So let's say that I asked you f at 2. So that would be the point that is on the graph. We're going to say it's 2, 2. Okay, so input is 2. It falls on the graph. So its output, we're going to say is 2. So that's the ordered pair 2, 2. That is what we're saying when we say f at c. C being the x value. Okay. Then what is the limit? So what is the graph doing as x approaches 2? So in that I'm saying, okay, from the left, it is approaching the same point, because remember, this is 2, 2, so it is approaching the output of 2. Notice that f at 2 and the limit when x is approaching 2 is equivalent, so this is what we call well-behaved. And it is, the terminology we'll use is continuous. So sometimes you'll be asked, is a graph continuous or not continuous? Whereas here, this would be a piecewise. If I'm tracing this, I have to pick it up and come here. This is not continuous.
So
the top one is. But if I had, where you do have to be careful, remember how we looked at some that had a hole? If I am tracing, I have to pick it up in the hole and put it back down. This is not continuous only because of that hole. Now, it's continuous at this point, but at this point, it is not continuous.
solid, right?
If that was solid, then you have an example like this where it's just solid. And then it becomes continuous. Okay?
Where does f of c come?
That just means whatever the equation is that gives you this graph. That's just your function or your equation. So this graph is your f at x. I just don't know what the equation is that makes that graph. All right. Then we're going to get into some consistent and basic limit properties or rules. And I'm going to give you some examples. Okay, these are the general forms, but you have to understand what the general form is asking. C is just some number. B is just some number. Okay, so an example where you would see this is if you saw something like the limit as x approaches 1 for the constant 2. So there's no x in there, as opposed to if this said the limit as x approaches 1 to 2x. So there's no variable, this is just a constant. It tells me that then that limit is equivalent to that constant value. So the answer to this would just be 2. If I had the limit as x approaches -5, and this was also the constant 2. It does not matter what it's approaching. If you have a constant here, that limit is just that constant. Okay? All right. Here we do have a variable, and it says x is approaching some number. We've kind of already dealt with this. You've heard me say direct substitution. So I'm going to say as x approaches 2, and then we have x here. All that means is just substitute that value in. So this would equal 2. But basically what you're doing is just direct substitution. All right, notice we have x raised to some power. So what would this example look like? If we said the limit as x approaches 3 for, say, x squared, again, all you're doing is direct substitution. So you would just do 3 squared. So your limit is 9. Yes.
So whenever you're writing like something like this, and as x approaches 3, we have to write like the brackets for the x squared.
The brackets don't have to be there.
Okay.
I just do it to separate it. But those aren't like, oh my gosh, they didn't put brackets, I'm going to count off. So if you wrote that with no brackets, we're good.
Okay.
Yeah. All right. So what we just talked about, and so we're going to get further in here, is direct substitution. Now, this is where you have to be careful, and you will see as we go, direct substitution works a lot of the time, but not all of the time. That's a teaser for the next page. All right, here's what's nice. Here I can look and go, okay, x is approaching 2. I can just direct substitute that 2 in for that x and do 3 times 2 minus 5. So 6 minus 5, 1. So that limit is 1. So what it tells me is that output they're approaching is a y. Remember, if you had a ordered pair, this is your output. So that would be, we're just not looking at it in graph form.
Then if you substitute back, it'll be 3 times 1 minus 5. Well, it's never mind.
Okay. Because I was like, I'm not sure where your head's at.
Yeah, that's
Okay. Okay. So let's just continue on. Direct substitution. I'm just going to replace. Now, I said this yesterday and I'll say it again. Once you're applying direct substitution, you drop the limit notation, right? I did not put the limit of 3 times 2 minus 5. When you use direct substitution, you drop that limit notation. So this would be the cube root of, I'm going to put 4 in for x, so 4 plus 4. So the cube root of 8, does anybody know what that is? What times what times what? It's 2. 2 times 2 times 2 is 8. All right, even when we have trig limits, we're still going to apply direct substitution. So we would have sine of pi times 1 I'll go ahead and write it, over 2. So I want to know what sine of pi over 2 is. All right, think your unit circle.
90.
It's 90 degrees, but I don't want degrees. Give me the ordered pair. What value?
The 0, 1. No,
It is
One.
0, 1.
Yeah.
So what would the sign be? The
Okay.
0 or the 1?
1.
1.
Because it goes to the y-axis.
Here's what she was doing in her head. Here's pi over 2. Here's the ordered pair. The x coordinate is your cosine. Y coordinate is your sine. So that's where we got 1. You were in trig last semester. You have seen that, and I would hope you would remember it. Okay, direct substitution, all we do, that's not hard. Bam, we're done. Now, this is an example that goes along with the rule or property number 1 that we just looked at, where if you have a constant, that limit is a constant. I'm going to give you the why behind that. If it clicks, yay. If it doesn't, memorize it until it clicks. All right, this right here is what we consider our f at x. So that tells me if I were looking at a graph, then f at x is equal to that constant 3. If I wanted to look at it as what we're used to seeing in algebra, that would mean the same thing. Okay, I asked you to graph y equals 3. What type of a line does it give me? It crosses the y-axis at, yeah, hint, hint, right? So it crosses the y-axis at 3. All right. So if I asked you 1, 2, 3, 4, the limit as x approaches 4 for that graph, that ordered pair is going to be over 4, what? 3. So what would that limit be?
7. No, wait. 3.
If I chose a number over here. So negative 1, 2, 3, 4, 5. The limit as x approaches negative 5, what would that be? So that's why the limit of a constant is just a constant.
Can you pick up random numbers from the pencil, the 4 and the maybe?
I just did.
Okay.
I just did, so I wanted you to see. I mean, if I chose this one, it's still going to have a limit of 3.
Okay.
That's going to have a limit of 3. All of them would. All right. Here, they are telling us the value of the limit. Whereas on the prior page, we found the limit. They're telling us the value of the limit is 7. That's just so I can show you these examples, okay? So notice this says the limit as x approaches some number 5 times f at x, okay? All right, so this is a constant in front of some equation. Well, with limits, what it tells us we can do is that constant can actually be moved out here. So in rewriting that, this would mean the exact same thing. 5 times the limit as x approaches c f at x. You can rewrite it that way. And they told us that this value is what? 7. So that would just be 5 times 7, 35. Again, I didn't have to find the limit. They just gave it to me. They said, here is a gift. Here, notice if we have a square root, or a radical, that is the same thing as taking the radical outside and having the limit as x approaches c f at x. So you can move that radical out. So this would just be the square root of, they told me that limit was 7. Here, if that is squared, you can actually rewrite it as the limit as x approaches c f at x squared. They gave me that as 7, so this is 7 squared or 49. That's just some additional properties. Okay. All right. Also with limits, so again, here's this where the limit of f at x is equal to 7. Now they're giving me a different equation, so they're calling it g at x, and they're telling me that is equal to 4. Okay, now here's the most important part I want you to get from this. So what this represents is if they wrote this at, well, I'm just going to rewrite it. Well, I'm just how do I do this? Well, I'll do this. Okay, as x approaches c, and that is f at x plus g at x. Now notice it's the limit, okay? So I don't have just, well, I don't even want to word it that way. Okay, what I want you to recognize is that we only have one limit notation. If my two equations are being added, or if it was subtraction, or if it was multiplication, even if it was division, you can actually apply that limit notation to each one individually. So you can separate it and put that limit notation with solely the f at x plus the limit as x approaches c to that g at x. That's what this is trying to get you to see. So what's nice is they told us what this limit was. This is 7. This is 4. 11. But more so than the numerical answer, this is what I'm wanting you to grasp from this, because sometimes we'll need to separate those. Okay? All right. Here, when we're dealing with composition, and I know you've done some composition, you saw that notation in Algebra for STEM. Okay, but now we're going to put the calculus with it with the limit as well. Okay, so here's what I want you to notice. Here it says the limit f at g at x. So think this. So what they've said is, okay, we're going to pull that, basically kind of think of that as pulling that f out and then applying the limit notation with the enter one. Okay, so think of this as f at, okay, so I look up here and this is the limit and I'm going to give you a value. I'm not going to do c, I'm going to say the limit as x approaches 1. And this is g of x, which is x plus 1. So if they gave me x plus 1, that's my g of x. I added a c just so we could see this work. Okay. All right. So think about this. This is just a limit. I can direct substitute. And when I direct substitute, I drop the limit notation. So I'm just going to do 1 plus 1, which is 2, right? So now what I'm left with is f at 2. So now I'm going to go to my f function, and that would be 3 times 2, which is 6. Okay. All right, so here it's the same thing, but they just switched that. So in this one, if you'll see, the G is pulled out. So I am going to do, again, I'll do the limit as x approaches 1. And for f at x, I'm going to put the equation that they gave me. So then I'm going to direct substitute. And when you direct substitute, you drop that limit notation. 3 times 1 is 3. So then I'm going to go to my g function. Whoops, how about times? No, sorry. I was looking up here. Here's my g function. So I was right the first time. Okay. All right. Now, for the examples that we did over here on page 1, notice none of them were rational equations. What do I mean by rational? Rats, it's a fraction. Yep. So now I have a numerator and denominator. Okay. So these are our rational expressions. Okay. Let's take a look at this right here. If I have a rational equation or expression, we have a restriction. What is always that restriction? The denominator cannot be 0. Okay. So when you look at just this and you're like, okay, I'm going to think through, the denominator cannot be equal to 0. So what value is restricted for x? -1. So x cannot be -1. That's my restriction. Okay. Is the limit approaching -1? No. So as long as it's approaching a number other than -1, I can just use direct substitution. So I'm going to substitute 0 in for every x. I'm going to drop the limit notation. So we would have 0 cubed plus 1 over 0 plus 1. We know that to be 1 over 1, which is just 1. So as long as what x is approaching is not that restriction, just use direct substitution. Okay, what about the next one? Can I use direct substitution? Yeah, that's not -1. So we would have 2 cubed plus 1 over 2 plus 1. So that's going to be 8 plus 1, 9/3, which is 3. We're good. Okay. All right. Dad nabbit. Now, here, y'all, perk up. If you don't want to miss this on a quiz or a test, you perk up because I get this answer every semester. I have students that will take this problem and tell me that's the limit. And sadly, I have to count off, and if it's worth 6, 7 points, you are already in the hole, 6 or 7 points. If direct substitution causes your denominator to be 0, you cannot use direct substitution. All right, so that means I need to start thinking algebraically, in particular, factoring. Now, I've thrown one at you that you don't see a ton of, because when I look at this, my denominator's not factorable. What about that numerator? What do you recognize? Anyone?
Conjugate? No.
No, that's if I was going to multiply by the conjugate.
It's one, and just so we can.
I want to think factoring, 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 trinomials, difference of two squares. Do I have squares? I have cubes. Can I do a sum of two cubes? I can't do a sum of two squares, but can I do a sum of two? Yes. Okay. So just for your memory, the sum or the difference of two cubes. Let's go through the general formula. Okay. So one example would be a sum. So that would be if you had a cubed plus b cubed. It is going to be a plus b times a squared minus a times b plus b squared. So a sum, it goes plus minus plus. Do you have any little jingles for that one to remember? Or do they just have to memorize it?
I'm just seeing so many things. I'm like, I gotta do more with that. You know.
So yeah. All right. Then the other one is a cubed minus b cubed. Because I'll be honest with you, even me, if I don't do a lot of factoring with cubes, I remember the a squared, b squared, and I always have to pause on, yeah, but do I add, or is it plus, or is it minus? This one is a minus b, but then it's a squared plus ab plus b squared. I wish it was minus plus minus, but it's not.
I had students who said something always positive in the back. Like they were like
They had a-
alternate,
Right.
but the back is always positive.
Oh, there you go. If it's plus, this first one is always plus. If it's minus, it's always minus. Then they alternate, except the last one is always plus. I like that.
Well,
I think that'll have it.
Had a jingle.
Yeah, I got no jingle for you, but still, I think that will register. Okay, so what that means is I need to determine what my A is and what my B is. Okay, so let's think what our A is for this. What times what times what is x cubed? X. Then we've got to consider what our B is. What times what times what is 1? 1. So I can rewrite this numerator as x cubed plus 1 cubed. So when I factor that numerator, okay, now I'm going to write this. Now, don't forget, we still are using the limit notation. So the limit, as x approaches -1, I am not direct substituting in this step, but I am going to factor the numerator. So I have a plus b, that's going to be x plus 1, a squared, x squared, minus a times b, x times 1 is just x, plus b squared, 1 squared is 1. We just factored that. Then the denominator is x plus 1. Okay, some terminology I want you to remember. We have determined that x cannot be equal to -1. What does that create? A hole in my graph. What we're looking to do is to remove that hole so we can find the limit. It's just been removed. So now we have the limit as x approaches -1. I've removed my hole and I'm left with x squared minus x plus 1, which means now when I do direct substitution, I do not get a denominator of 0. So I'm going to drop my limit notation. So I have -1 squared, that's 1. plus 1 plus 1. So what I know is when x is -1, it's undefined. The limit, so the graph from both directions is approaching the output of 3. So this was technically in my graph a hole at that point. So remember when I made it, well, in fact, I think I did this. This is that graph. This is the point -1, 3. It has a hole. We removed that hole to find, notice the limit, it is approaching the output of 3. It is approaching 3. So we were able to find the limit without looking at the graph. Okay? All right. Let's see what time it is. Okay, so now you mentioned this word earlier. I have a radical, yeah, so I am going to have to, I got to eliminate the radical. So I'm going to change this equal sign to a multiplication. Okay, so some might initially think, okay, I'm going to multiply times x plus 3. Is that going to remove my radical in the numerator? That's not the conjugate I want. I want the conjugate that goes along with the radical. All right. So I'm going to multiply the numerator times x plus 1 plus 2. And technically, I'm multiplying times 1. That's why it's over the same value. Okay. So think conjugate when you have a radical. Okay, this is the limit as x approaches 3. Now, why are we doing this? I should have mentioned this first. Why are we doing this? Because,
We can cancel the square root.
well, ultimately, but I had to do this because this is approaching 3. 3 would make my denominator 0. If this was x approaching 2, I wouldn't have to do that. Okay, but since it's approaching the number that makes my denominator 0, I have to do this. Okay, why do we do the conjugate? Because that, when we FOIL, it will eliminate your O and your I, right? They'll be opposites and they get eliminated. So I'm only going to look at first times first and last times last. All right, so first times first is multiplying a radical times itself, which just means it gets rid of that radical. So I'm left with x plus 1. And then I'm going to do last times last, -2 times +2 minus 4. Now, in the denominator, I'm just going to write the binomial x minus 3 times the square root of x plus 1 plus 2. I'm not going to go through distributing that because I don't think we need to do that. Okay? All right, look in your numerator because I still want you to notice as x approaches 3, we still have this problem right here because this makes my denominator equal to 0. But look at what is 1 minus 4. So this simplifies to x minus 3, correct? What can we do now? We can remove that cranky part of the denominator that is causing our denominator to be 0. Now, here's where you need to be careful. What is left in the numerator? Because it's all gone. What's understood if you cancel everything out? 1. So we have 1 over the square root of x plus 1 plus 2. We have removed that whole, so now we can apply what?
We cannot have a radical, right?
Yeah, we can have a radical.
The denominator?
Sure. Unless it made it 0, but we removed that whole.
No, we can
What
do
process have we been using once that gets removed?
direct substitution.
Direct substitution. So now I'm going to directly substitute everywhere there is an x. Now, I'm direct substituting, so I'm going to drop my limit notation. So I have 1 over the square root of 3 plus 1 plus 2. I have 1 over, and they were nice to us. 3 plus 1 is the square root of 4, which is 2. So I have 2 plus 2, I get 1/4. All that work to get to 1/4. Okay. All right. This example is just showing you some notation that you might see. And it's this triangle with an X. That is, the correct notation for that is called delta X, is what we call that. It's just like another variable. So if I put the variable Z there or whatever, it's just another variable. Okay. But it's something that you're going to see. All right. So when I look at this, I'm like, okay, delta X is approaching 0. Well, I know that delta X, what number, if I substituted for X, would give me a denominator of 0? 0. So delta X cannot be 0, so I cannot use direct substitution. So I'm going to start exploring. Well, I notice a 2 outside the parentheses, so I'm like, I think what I'll do is just distribute that and see if that is helpful at all. So now I have 2x plus 2 delta x. Y'all, 2 delta x just means you had delta x plus delta x gives you 2 of them. Okay? And then we have minus 2x, all of that, delta x. All right, what do you notice in your numerator? 2x minus 2x is gone. So technically we are left with the limit as delta x approaches 0, and we have 2 delta x over delta x. Okay, well, if delta x is just considered a variable, that's not any different than 2p over p. If I gave you this, what would you tell me I could algebraically do? My p's would cancel, right? Same thing here. Those cancel, so we have removed that denominator of 0. So technically I'm left with the limit as delta x approaches 0, and I'm left with the constant 2. Oh my, what was that property? The limit of a constant is always flip back in your notes. We did it. The limit of a constant is always equal to that constant. So what will this equal?
2.
Which is 2. If this would have been a 7, that would equal 7. If this would have been 299, it would equal 299. So the limit of a constant is always that constant. Okay? All right. Look at this one. They give me f at x. That is 3x plus 2. And it is asking me to find the limit as h approaches 0, f at x plus h minus f at x. Okay, well, here's f at x. That's 3x plus 2. So in place of this f at x, I'm going to put 3x plus 2. But I also need to know f at x plus h. So I'm going to take the equation given, and everywhere there's an x, what am I going to replace it with?
For 3x plus 2.
Well, so I have 3, and what are you going to put in place of that x? What's my input? What's inside the parentheses? X plus h. So what this is telling me is everywhere there's an x, I have to replace it with x plus h. And then I still have that plus 2. So now I'm going to distribute my 3. So why did we do that? Because in place of this f at x plus h, I'm going to substitute it with what that is, 3x plus 3h plus 2. So I'm going to rewrite this as the limit as h approaches 0. And in place of, I'll do this. In place of this, I'm going to put this. Minus, and in place of this, I'm going to put this. Sorry. Now be careful, there's a minus, so I have to use my parentheses 3x plus 2 because you have to distribute that negative through. All over h. Now why are we doing this? Because if I direct substituted, I would get a denominator of 0. All right, so let's simplify the numerator. I have 3x plus 3h plus 2. Now I'm going to distribute that negative through. So I have minus 3x minus 2. All of that is over h. Now, do you see how that was helpful? 3x minus 3x subtracts out. 2 minus 2 subtracts out. So we are left with the limit as h approaches 0. In the numerator, I'm left with 3h over h. Oh, lo and behold, what can I do?
Cancel out the H.
I can cancel out my h, so I'm left with the limit as h approaches 0 of a constant 3, and the limit of a constant is always that constant. Okay? All right, we're going to quickly do these 3 and then we'll stop. All right, this is saying the limit of the trig function sine of x. Y'all, you just use direct substitution. So example, if I had the limit as x approaches, let's say pi, and I had sine of x, all you have to do is direct substitute this. So when I direct substitute, I remove the limit notation. So I want to know the sine of pi. The sine of pi, is it -1 or 0?
No, wait, not 0.
0. Think cosine comes in the alphabet before sine. So cosine's always the first one. So the sine of pi is 0.
That was the y one.
For sine, yeah, because S comes after
Oh,
C. Yep. All right, here is the exact, basically the same type. So this would be the limit, say as I did, x approaches 2 pi for cosine x. Just use direct substitution. So you would directly substitute that, drop your limit notation. So we want to know the cosine of 2 pi. 2 pi, cosine is your x coordinate, which is 1. Then, though, we have tangent. So the limit as x, say, approaches pi over 4 for tan x, direct substitute. So this would be tangent of pi over 4. So it's tangent now, so you can't nice and neat go to that. You could go to your calculator. Just be sure you have it in the correct mode. Does anybody remember what do you, one is correct? Okay.
Yeah.
Uh-huh. Yeah, be sure your calculator's in radians. So, all right, that's where we're gonna stop today. So I will update the announcement when I get back to my office. We are looking at the quiz